you may start.
Thank you very much. So this is like my first NullCon. I'm very happy to be here. So thank you for having me here. So let's jump right into the talk. If it's possible, dimming the lights would be great, because A, you can see the slides better, and B, I'm still a bit hangover from the party yesterday. Well, all right, let's jump right in. So XNU heap exploitation from kernel bug to kernel control. So the topics of this talk are a brief introduction into XNU, a brief introduction into mock ports and heap zones like calloc and zalloc. And then I will talk about treadmill, which is my exploit for a bug. And then I will walk you through Vintex and Ventex, which are two exploits for a different bug. By the way, slides will be available later, so you can reread them. So goal of this talk is to introduce you to some aspects of XNU and get a general idea how to go for exploitation, present real-world techniques like real-world exploits, and walk you through these exploits. So not goal of this talk is to understand every single aspect of XNU mentioned in this talk, because I only scratched the surface myself. And you also don't need to understand every single line of code in the exploits or what I show you here. Just try to understand the general idea behind it. And if you can't read it or are not sure what it's about, just don't get lost in the details. Focus on the general thing idea. And it's good. So I only read on reverse XNU enough to make this exploit work. So some information presented here is good enough to explain why it works, but it may not be 100% accurate in terms of it may work slightly different, but like this simplification is good enough. So some things might be oversimplified, so keep that in mind. But in my opinion, this is the way to go for exploitation. Because it's a time-benefit trade-off. If you make an assumption it could work that way, then you test it works, good enough. Doesn't really matter if it actually works like that, but if you got your stuff to work, that's good. So another disclaimer. If you can't follow some things, that's fine. Don't get lost. Follow the bigger picture. For further understanding, I recommend rereading the exploit source code and the slides if you care. So, mock ports. This part is mostly taken from the blog post from blog 360.cn. What is a mock port? Mock port is a one-way transmission channel for mock messages. There is a single receiver, and there can be one or multiple senders. So in the kernel, these are represented as IPC port structures. So writes to the mock ports are stored in an independent process IPC table. So every process knows what send or receive writes and has to what ports. So these are used for inter-process communication, and tasks, as they're called in mock, which are represent the process, are represented as mock ports. So every task has a port and a handle to it. Send writes to a task port means full control over the task, because these are special. So you can send messages or use the API to read and write memory, create and control threads. You can handle exceptions and much more. So a send write to a task means you have full control over the task. TFP0 is short for task for pit 0. So the goal is to get a send write to the kernel task port. This will allow you to read and write memory. This is what we want to achieve with our exploits. So let's talk a little bit about heap zones, because we're going to do a lot with the heap. So there's zalloc. So the kernel heap is divided into so-called zones. And each zone kind of allocates pages, and pages can be, and zones can split pages up to allow sub-allocations of smaller size. So there's a wrapper, there's different zones. For example, calloc 16, that's the name of a zone. It divides the page into 16 byte chunks, and these can be allocated individually. So this is managed by calloc. Important thing to note here, zones are garbage collected. So freeing all calloc elements in the page does not guarantee the page being freed from the zone. So we need to keep that in mind when exploiting. Calloc is a wrapper for zalloc. It manages multiple zones. So as a programmer, you just call calloc in a size and it gives you back memory. But internally what it does, it figures out in which zone to place the allocation, and then like allocate the memory. So the thing with calloc is when you're freeing the memory, you need to remember the size of it so it like frees back into the correct zone. So when passing k free, just the pointer and the size you allocated it with. And this already brings us to our first bug. So this is taken from the blog post written by Luca Moreau. I dubbed my exploit treadmill, but they dubbed the bug lightspeed. And basically, what's the bug about? So, very brief introduction in the bug. There's a thing, like a function called list.io. And this thing can be called in two modes, basically synchronously and asynchronously. So for the synchronous way, it would go get user input, do stuff, and at the end checks one if condition, and if IO context IO issued is 0, free IO context, and then freeing the object. For the asynchronous path, similar, get user input, do something asynchronously, but then check the condition, and if IO issued is 0, free the thing. So the issue here is that the asynchronous function might call free, and if that happens, then we have a double free, because then the asynchronous function frees it, and like this function frees it up as well if the condition is satisfied. So how can we trigger that? We call list.io in asynchronous mode. We hope for the worker thread to finish before the thread that spawned the thing reaches the statement where it checks if the context IO issued is 0. Then that thing gets freed. We reallocate it with the second word set to 0 to satisfy that condition, and then the buffer gets freed again. So in this block, they provided a POC to trigger it. So that's very simple. Thread 1 basically in a loop calls that function asynchronously. Thread 2 does like a syscall to allocate a calloc 16 buffer with the word set to 0, which they do internally with the poll call. And that just kernel panics the device. So this is like my starting point where I started. So the exploit plan turned this double free into use after free, and you want to overlap the useful object with controlled data. You want to use the bake object to get the kernel slide and get the kernel read-write, and finally manage to somehow get a send write to the kernel task board, which is like get task for bit 0, which is our total goal of the exploits. So I talked to little Lilo, and he suggested to spray out-of-line MAC messages for exploitation. So I'm going to talk a bit more about MAC messages to understand what's happening here. So you can send a MAC message to a MAC port, right? The sender does not need a port to identify. Like, you don't need to say, hey, I'm this. The issue with here is that usually want to use that to call an API in a different process, but usually want to have a response. So what's being done here, when sending the message, you append to the message a send once write to a port the other process controls. So the process you call into has the send once write, and he can reply with the message exactly once. Optionally can send more ports. When I say sending ports, in reality is send a write to a port, and this write can be a receive write or a send write. There's actually more than that. You have like different types. You can say, I have this port, I give the send write to you. I can give you a send once write. I can move a receive write. You can copy send write, so there's like you have a send write and me have a send write, but you cannot move. You cannot copy a receive write, because remember there can be only one receiver. But you can like have a port and move it over to someone else, and he kind of owns it now. So ports can be sent inline and out of line. So if you recall zones, MAC messages and MAC ports, they have dedicated heap zones for that, which means in that zone, only MAC ports live, only they can be allocated in that zone. But MAC message out of line buffer goes into a calloc zone, and in calloc, lots of things can be allocated, like generally everything you'd use like malloc for in the kernel use calloc. So if it falls into a calloc zone, we can potentially allocate something useful. To show you the difference, at the left we have an inline message. So you have the header, the body, and I send like port descriptors, 3 port descriptors inline. And it's like kind of pointers at the time it gets to the kernel, which point to a MAC port. Versus an out of line, you have the header, the body, and you say, I'm sending these out of line. So that thing contains a pointer to a calloc buffer, and the calloc buffer just has pointers to the port. And this calloc buffer, this is the one we're going to target. So when sending MAC messages with 2 out-of-line ports on 64-bit devices, 2 pointers, 8 bytes, it's 16 bytes, so that goes into the calloc 16 zone. We can set the first port to be MAC port null, which nulls the first pointer. So the first keyword is 0, and that satisfies the condition relocate buffer with second word set to 0. It's actually like second 4 bytes, 0. So, all right, we satisfy that condition. And the second port is a send write to just some port. So what we're doing, we have 2 threads. One thread triggers LIO list.io double free buck, and the other continuously spray out-of-line ports, keep sending messages with out-of-line ports. Let's say OX 4000 for no particular reason. For things like that, you just like generally trial and error and figure out what the best number is. So essentially how it looks like in memory, MAC message gets allocated. Then the out-of-line buffer get allocated. We keep sending, more MAC messages get allocated. More out-of-line buffers get allocated. And at some point when you allocate a MAC message, a LIO object is allocated in calloc 16, and then it's freed because the asynchronous thread finishes. But then, because of the message we send, we reuse the same buffer, like the allocations happen to fall into the same slot. And the OL buffer is there where LIO list.io lived. But because of the bug, that memory is freed again. So we have like a dangling pointer. But if you keep spraying messages, what happens is we allocate more messages and more out-of-line allocations. So if you like keep doing that, at some point we have 2 messages pointing to the same buffer. So a different view of that is kind of like that. So if you have a port and you send a send write to itself, you can like check the handles. You compare the one you're receiving the message on and the actual handle you received. If it's the same, then we have like the situation on the left where it's like 1-1 or 2-2 or something like that. So you receive them in order and expect the first port in the message to be MAC port null, because that's what we send it to. And we expect the second port to be the same one as we receive on, because they have like the same handle, because this is one we send. This is true for all, but for the one where it overlapped, because the latter message overwrote the earlier one. So if we receive on port 3, we will get back the handle 4, and since they get freed when we receive them, handle 4 will now have a dangling pointer pointing to something that's freed. So the next stage of this is every time we receive a message, potentially this could be our target message, the one where the bug like gripped. So every time we received, we're going to spray OS data objects to again reallocate that heap region. So this time I set the second 8 bytes to 0 to make sure, like just for debugging, and the first byte is a pointer to your MAC port. So when you now, like, you know that the handle 4 has a dangling pointer which like potentially got reallocated, and then when you receive on handle 4, it will get a handle to our fake port. And this is good, because now we have a handle to a port we control. Receive the MAC messages where the out-of-line buffer pointer points to our control data. We get a port descriptor to our fake port. So here in this particular exploit, I use an iPhone 5S, which does not have PAN. So PAN is privilege access never, which is like SMAP on x86. So this protection is not in place, so I can just spray user space pointers and I can dereference them from kernel mode. So I put the port in user space and did exactly that. And having like this, you can pretty much just copy and paste Vortex. Like Vortex by Zigusa, he like laid it out, and after having like this primitive, you just go there. I will go into detail what like all of these steps means when talking about later exploits. Basically, just real quick, you leak a heap pointer to a real port, you keep leaking pointers, and then you build a read primitive using get pid for task, same as like the previous iOS talk mentioned. You leak the KSLR slide, build a kcall primitive on devices where you can, like now with pack it's more difficult, but back then it was super easy. Kcall also gives you a kwrite because you can jump to a gadget which does a store. And yeah, that's kind of where to go. The issue here, if you like just try copy and pasting that and the part from Vortex, is that here we spray send writes to a port and not a receive write. But for Vortex, we actually need to get a receive write because we need that for doing registering that notification, and we can't like call that function without having a receive write to the port. So the way we do it is we receive on the port and expect to receive the same handle. We can't do that for a receive write because like we can't have two receive writes, and if we send away our receive write, we cannot receive messages anymore. But the solution to this is like quite simple. Just keep two lists. One list for where you receive the actual message on, and a different list where you give away the receive write. And for the one where we give away the receive write, we actually also need to keep the send write to that port, just that the port keeps the handle so we can recognize it later. So before it looked like this. So starting from the green, mark message gets sent to the blue mark port. It contains an out-of-line buffer, which also points to the mark port. So when we receive it, we check if the P thing that we received is like port 1, pretty much. After we change it, we receive like on port 1 index I, like we keep two lists, send a message over, and we expect it to be port 2 index I. And if it's a different one, then we found an overlapping thing. So if you want to go with pan, you would like spray first, like get the setup, but then instead of spraying user space pointers, you would continue and receive the other message. So the buffer gets freed again, and you won't reallocate again with the real mark ports. Now then you have a real pointer, and then you can use your OS data primitive to read back the pointer, and then you can leak the pointer, increase it by, I don't know, some page size, and increase it by 64 pages, and then you have a rough idea where in heap some allocations will be happening. You try to spray there and put the fake pointer there. I don't want to go too much into detail with that, but like maybe for rereading the slides. Yeah, a pan-less version was chosen because Calog 16 is very noisy, so every time you do a reallocation, if you don't actually allocate a slot, but something others takes that slot, your device will panic. So, and there's a lot of allocation happening. So if you want to go for the painful version of this exploit, it's left as an exercise to the reader, but like, it is as painful as it sounds. Spawning and suspending threads might help to increase the success rate. Just run your own experiments. Also, real quick, there's been a pan bypass by Zigusa. Basically, what allows it to do is to have a read-only page in user space and have the kernel like being able to dereference and read from it, even with pan. The issue here is that the kernel actually can't write to it due to the nature of this bug. So it's not as trivial to use that with the primitive, because we actually need to write to these ports, but maybe you can figure out something with that. Just wanted to show that's a thing. Let's jump into the next bug. So this was also taken from blogs 360CN. And it's the IPC voucher use after free, or maybe you know it from me and Beard's voucher swap. So basically, this is the code in MIG. It has a bug. It's pretty hard, like it's not obvious to see what the bug is. The problem is in assumptions that are made around that thing. So MAC is MAC interface generator. It's too complex to cover in this presentation. I have no clue how it works because it's like a bunch of like printfs that generate your C code from dev files. And basically what it gives you, it's like an easy to use functions which use Mac API into the hood. Say you have like two processes, you want to like kind of run a server and they communicate over Mac to being able to call a function in there, you can use that. So when running my experiments, I was like trying things out. So I talked to Zigusa. He sent me this piece of code. He was like, these, what's that, like 5-6 lines of code. And he was like, yeah, it's super easy. Just run mic codes def, and then you get, holy shit, like a lot of code. So how much code is that? It's like 822 lines generated for you just from like these 5 lines of code. So it generates a lot of code. It's very complex. So the thing is, it has a set of rules and assumptions, and things break when these assumptions are invalidated. And this is what happened here. It's not due to the code, but the code was doing something which broke assumptions built around mic. But I really don't want to focus on mic. Let's just jump into the POC, because this is as much as I like looked into mic just for this presentation. So sorry, my bad, tweeted this screenshot. It's actually a screenshot, so I can not make it like bigger or better readable, but that's fine. So this is what I used to get started. I typed it on my, run it in Xcode, run it, and it crashes. Perfect for me. So let's examine this code. If you can't read it, that's fine, don't worry about it. Basically, we have 4 primitives which this POC gives us. We can create vouchers. Like we can allocate them. We can register a voucher to a thread. All right, cool. We can free a voucher by using this bug by decrement a reference. It uses reference counting internally. And we can somehow access the dangling voucher. This is all we need to get started. So the exploitation plan for this is get a dangling voucher pointer. So just alloc the voucher and drop an extra reference. Then somehow release the page from the voucher zone, reallocate the page in a zone and fill it with controlled data. Because remember, there's like different zones, and if a page belongs to one zone, you can't alloc other data in it. Leak a pointer to a real IPC port, modify the pointer, craft fake port and kernel, and get a kread primitive, right? Sounds easy enough. All right, let's see how we do that. So for the Vintex exploit, we're doing as following. This is memory. That's your RAM. Memory is divided into pages. All right, good enough. Some pages are already allocated, and sometimes there's like holes in it because like it's not consecutively allocated. We don't really know the state, but we assume we have some kind of state like this. So what I'm starting to do is I'm starting to allocate vouchers. I'm calling them GC vouchers, but really I just like call an API to know they're allocated in the kernel. So we allocate these so-called GC vouchers, starts filling the holes. And then we allocate the before vouchers. The main purpose of them is to fill the holes, so we can assume starting from now we have like linear continuous space, and we hope it's like that. Before vouchers don't necessarily fill up the full page, so we can have something like this. So then we allocate our target voucher. This is the one we're going like use the bug on. And after that, we allocate after vouchers, because what we need to make sure is that all allocations in this page belong to us. We can't have that another process allocate something, so we hope this is the setup. We allocate more after vouchers. So when dropping an extra reference on the target voucher, it gets freed. So you see it's black. Now what we're going to do is we free all before vouchers and all after vouchers. But just freeing them, they're probably still in the voucher zone. Because as I mentioned before, these things are garbage collected. So just freeing every element doesn't mean we release the zone. And we need the zone to be released. Like we need to release the page. So now the GC vouchers come in place. We free the GC vouchers to have them A at the very top of the free list in case there is such a thing as a free list, which I don't know. And B, they also hopefully like at lower addresses in memory as everything else. So these are the two assumptions I make. So the assumption is then when I do an allocation next, hopefully it will be one of the GC voucher slots reused. Now we trigger a garbage collection to reuse unused pages, but how exactly do we do that? Well, we can slowly allocate vouchers, and each time we allocate a voucher, we measure the time. So when we see a peak in time, we can use that as information that the garbage collection did its job and the pages got freed. Quick note here, if you have another huge time peak, that could mean that you actually allocated more pages, which you don't want. But basically using this timing side channel, you can figure out when the garbage collection did its thing and stop allocating. Now we spray controlled data and hope it will fall into the same page where our voucher was. We release the unused GC vouchers because we don't care anymore, and we don't want like memory pressure because there's no swap on iOS. Now we read back the dingly voucher, and the thing with the vouchers is they have like a field, like it's a struct, and if it's 0, like null, which we can force, we just spray like 0, and it reads it back. It says, hey, there's no like port, so I will allocate one for you and store the pointer in there. So by reading it back, it makes a new allocation and stores the pointer in there. So by reading back the OS data, we actually leak the pointer. And the dangling voucher can fall into several places. Can either be old page or new page. Here, I just assume it's like behind our things. It really doesn't matter. We could like increase likelihood of also spraying ports, but here I just assume it's like that, and go from here. So this is the setup we have right now. We have a heap pointer to a real port, so we know where this PT thing is. What we're going to do is we allocate more ports. So next we want to increment the pointer by enough pages and align it to a start of a page. This is done by freeing the OS data and reallocating back and hope it falls into the same slot. This is how we like modify the data in the VT thing. Then we hope it points to the start of an unused, unallocated page. Then we allocate more data, but this time fake ports, and we hope that the pointer we sprayed before now points on this fake port. From here, let's take a look how Vortex does k-read. So having a fake port pointing to a fake task, which resides in the same data buffer, that's the way Vortex does it. Then we use the fake task, the task BSD info member, to overlap with the fake port's context member, because we can use pit for task to dereference that field and read 32-bit. And we can use an API, port set context, to modify this context. So we can, from user space, call the one function to set a pointer and call the other function to read from it. Pretty convenient. The issue here is that for setting the context, we need a receive write, which we don't have here. And unlike the exploit before, where we can like do some trickery to actually receive write, we can't do, due to the nature of how vouchers work, we don't get a receive write. So we get to live with the send write. We need to figure out something else. What we can do is we make the fake port's k object overlap with the real IPC port where we do have the receive write. We can then on these ports set the context member and do the same trick again. There's just one constraint when like pointing that to arbitrary data. We need to make sure that the reference count is not 0. Let's see if we can satisfy that. So what we do here, like all the ports we sprayed, we actually sprayed receive writes because we don't need to, we sprayed ports where we do have receive writes to them. So this is how the ports look like in the page, or just one page. So this huge struct is like the K port T. It's not taken from the XNU source code, but it's like the one we just implemented. So it's sizes and fields, everything match. Basically, we have like one field, which is IP context, which is about here. If we take a K task, which is the other thing, and make sure that these two overlap, we have something like that. So we would point there, so these two align and overlap. Now we need to make sure that the reference count is non-zero. So this actually overlaps with way different port with the IP requests field. We need to make sure this is non-zero, and here every value works. So ktest reference ref count overlaps with IP request. To get a valid ref count in iOS 11, IP request needs to be non-zero. So any pointer value, like anything non-zero, is fine. We can do IP requests on all sprayed ports. We can just port set attributes, and it will cause an allocation and store a pointer there. So for the Vintex K-read, we just, if you can't read it, don't worry, but I think it should be readable, right? So mark port set attributes on every port we sprayed, and then we can pit for task to read back. Fake port points to fake task with overlaps with real port. Yeah, because we already know the pointer of a real port, the one we leaked at the very first stage. And then if we just subtract the size, we get a different one. And then that's good enough. Now we can k-read, right? Set a pointer with port set context for all the ports, and then use pit for task to read it. So this is actually quite slow, because since we don't know which port exactly is the one overlapping, we need to set that thing on all ports before we can do a 4-byte read. Now we got k-read and a pointer to a real port with receive write. And we can proceed with Vortex to leak IT key space, self-task, IO surface root user client, the port, the C++ object, and the vtable, and then going through the vtable, we can leak the kernel base. As already presented in the jailbreak talk before, basically you just have this allocation, and you leak up the pointers. There's like a hierarchy of pointers, one object saying I belong to this, I belong to this, so the port belongs to the space belongs to the task. If you know where the task is, you can call an API saying mark port registers, which writes a pointer into that task struct. From there, you just read at an offset, get that pointer. So you leak the port of an IOKit object. That one has a port to a C++ object. That has a vtable. And reading the vtable, it points into the kernel text segment. And from there, you can just keep reading until you find the kernel header. And that's it. So, Ventex. iOS 12 added ref count mitigations. So OS ref count T allowed range is from 1 to OX0FFFF. So we have 7 Fs, not 8. If the ref count is outside of this range, it just panics. So if we overlap with the upper part of the pointer, it will always panic. And in the lower half of the pointer, it will panic in some cases. And if we do lots of allocations and the virtual address grows, then it's very likely that it panics. And since we do have a lot of allocations, we just assume that like we can't do here. Also, there's another reason why we want to move away from this overlapping technique, because if like Apple changes a struct, introduce a new field or something, then all of that falls apart. So it's like really hacky. So Bazat used a different approach with his exploit. So he used pipes. So after he released his exploit, I was like, hey, pipes are really cool. So I was like, all right, let's use pipes. We want to move from Vintex to Ventex, which is just the same exploit, but for iOS 12, but that thing changed. We're going to put the fake port and the fake task in a pipe buffer instead of OS data. That allows us to safely read and write that buffer without having to worry of reallocating it. We don't need the port set context tag anymore because reads and writes are safe. So how does it actually work? POSIX programs, as you know, use file descriptors. Default ones, stdin, stdout, stdr. Pipes give you an input and an output descriptor for reading and writing. So you write into the writing end and you can read from the reading end. And then you have two types of pipes. You have the blocking pipe, like the default one. The write calls stalls until you read the data. And you have the non-blocking pipes. So the write finishes and it stores the data in the pipe, and then you can later read it back. Blocking read, it just goes through. Non-blocking, you write, it's in there, you write more data, then you idle, it's still there, and then you can read it. So non-blocking pipe allocates a buffer in the kernel which is big enough to hold the data. This allows to make a controlled size allocation by writing data in the buffer. Like if you write little data, it's small allocation. More data, big allocation. Reading data, just read it back from the pipe. And how do you modify it? Well, you read it first, then you write it back in, and it will stay in the same slot as long as you don't change the size. So back to step 11 of Vintex. We have a heap pointer to a real port. Now, this is also, until here, it's the same step for Vintex. Now, we increase the pointer by enough pages, align it, and now the difference is that we spray pipe buffers with fake ports. So you can see the red thing there is the fake port, and the fake port points to a fake task which resides into the same pipe buffer. So kread now read the buffer data from the pipe, modify that pointer, write it back into the pipe, and use pit for tasks. So this is a pretty solid way of kernel read. What next? Well, we have controlled fake port, we have a kread primitive, and we have the KSLR slide, as I already showed you before, how to get it. What we want is a proper kernel task. And what we're going to do is we're going to continue Vortex style. We're going to read the kernel zone map address. So it's in the data segment. Once you know the slides, you just read a data segment and you get a pointer. You update the fake tasks zone map. We didn't need to do this before, because before we really only cared about like two fields, like ref count and the pointer we want to read from. But now you put in like a map. So that thing actually belongs to a map. So then we can use that fake port fake task to remap that memory we were using to user space. There's a Mark VM remap, and now we like shared mapping between kernel space and user space. That's not so important for Vintex, since our reading and writing primitive inside that buffer is already safe. But like it's important for Vintex, because for Vintex, every time we would need to do like it was slow, we had to do like this hacky thing, and so Vortex did it like that way. Just remap it, and then you can just write to it. So next we're gonna dump the vtable, the full vtable of IO root, IO surface root user client. In our fake port, we changed the type to IOKit object. So it was a fake task before, and now it's a fake IOKit object. So why do we do that? Well, the port has a pointer like object. So we set the object pointer to point to our fake C++ object. And that fake C++ object points into our fake vtable. So in that fake vtable, we modified one pointer to create a kernel call primitive. So by using the IOConnectTrap6 function, we can jump to what like we put into the pointer, and we control arguments like with some hacks. We can like do a kernel call primitive from this. And yeah, we just continue from here. Vortex still. There's a really good write-up on Vortex, so you should read it if you haven't. Basically, what we're going to do is we replace the process credentials with the kernel credentials. That will allow us to call setUID0. setUID0, like calling it that way, has the advantage that it also updates Mark tasks, like internal Mark stuff. And this allows us to get the privileged Mark host port. Why do we need that? Basically for easier retrieval of the kernel port later. Basically, we find the kernel task, like the real one, in the kernel, because we have the kernel read. We remap the kernel task to a different virtual address within the kernel. This is done to bypass some mitigation, where they block certain APIs from being used with the kernel task port. But like remapping it is a different pointer. Pointer compare doesn't work anymore, and we're good to use those. So we have like this remapped kernel task, and then we store the cloned kernel task pointer into an array, hosts special ports. So now every root process, I think you do need an entitlement, get task low entitlement. If you root and have that entitlement, you can call host special ports index 4, and it will give you back a kernel port, a Centroid2 kernel port. After this, we're like pretty much done. Just clean up the exploit, and we achieved our total goal. So to conclude this, we introduced you to XNU heap zones, a bit of Zalog and Calog, talked about heap exploitation techniques and strategies, introduced you to MAC ports, and outlined its importance for kernel exploitation. If you want to go into iOS or XNU exploitations, MAC port is the way to go. There's a quote by a friend, was like, every time Apple introduces a new mitigation, there's a MAC API to bypass it, most likely. So keep that in mind if you're looking at new stuff. Yeah, we had a full walkthrough of 3 kernel exploits for 2 kernel heap bugs. Pro tip, always turn your primitive into use after free and type confusion if you can. I know like with the newer processes, with PAC point authentication codes, it might not be possible, but surprisingly, the out-of-bounds timestamp exploit, it replaces a pointer, and that works on PAC devices. So just use after free type confusion, replace pointer, will fake MAC port, and you're good to go. For better understanding, you can reread Treadmill, Vintex, and Ventex. And yeah, slides will be available. I'll tweet a link, and probably Nolkan will tweet something. And now we have time for questions. Thank you very much for listening. So, are there any questions? Probably a lot of information, very packed time, so need to think through. Yeah, you can talk to me also later. I'm available today, so just catch up.
Quick one. Do these techniques work on macOS as well? Because you're trying to get tasks for PID on macOS as well, and with SIP, you're kind of denied that. Do you have any techniques that could like bypass?
So the thing presented here, it also works on Macs, because yeah, like you use the low-level API.
Because the goal is to get a send right to a task port, right?
Yeah, send right to the kernel task port, and using this remap trick, it's actually, so the kernel, there's a check, there's APIs for it, like reading and writing kernel memory, and they check, we don't allow that for the kernel task port. But if you remap it, you bypass that check, and then it still works. It works on Mac, on iOS. These exploits, Vortex, have been ported also to the Apple Watch, and Ventex, the updated, was not by me, but by someone else, also ported to the Apple Watch. So basically, yeah, XNU. That's why the talk is XNU, not just iOS. I think there was another question somewhere here. Okay.
Okay, thank you, sir.
Thank you.